Okay, for this video, I'll be going through pure physics kinetic particle model of metal tutorial. Okay, question 1, describe the arrangement of the particles in the solid. Okay, so we are talking about the arrangement. Now, the particles are very closely packed and arranged in a regular pattern. Okay, in the case of the liquid, the particles are less closely packed than the solid. So sometimes you may need to write this. Okay, and arranged in an irregular pattern. And for gas, the particles are very far apart in an irregular pattern. Okay, question 2, describe the movement of the particles in a solid. So the particles vibrate about fixed position. So this is their movement. And for the liquids, they slide over each other throughout the liquid without fixed position. And for the gas, they move freely in any directions at high speed. So sometimes the question may lump the arrangement and the movement together. Okay, so it is up to you to write down clearly. If let's say they want to ask you to compare between the solid and liquid, right? Compare the arrangement and the movement of the solid and liquid particles. So if they just give you a lot of blank space to write, you may want to write the arrangement. Okay, arrangement of solid, and then arrangement of movement of the solid, and then arrangement of liquid, or motion of liquid. But you must be very explicit to say that you are talking about the arrangement and the movement of solid, or arrangement and movement of the liquid. Okay, so you cannot just say particles are very closely packed and they are also less closely packed. You cannot just lump them without stating which is which particle. Okay, now choose true or false for each of the following concerning the Brownian motion. Now it's due to the random bombardment of smoke particles by the invisible air particles. That is true. It's due to the vibration of smoke particles at a specific temperature. That is false. Okay, so Brownian motion, basically it is by the invisible particles. Okay, they are in constant random motion, and since they are invisible, we need something visible. So we can throw in some smoke particles which have a low mass or small mass, okay, and are visible. Okay, so all these invisible particles like air or liquid particles, they will collide with the low mass visible particles to make it seem like the smoke particles or the suspended particles are actually moving about on its own, but it is actually due to the air particles or the particles surrounding it. Now, it's due to the strong attractive forces between gas molecules and smoke particles. That is false. There's no force of attraction. So figure 4.1 shows an experiment to observe the Brownian motion. I recall seeing a very old O-level question asking students to draw the setup. So firstly, we need a lamp so that it can illuminate what is inside the air cell. So in this case, air is inside, but because air particles are not visible, right? So we have some smoke particles. So again, they are low mass. Okay, their mass is low, they can be knocked about, and they are visible under light. Okay, so we still have to use microscope to take a look clearly. Now draw a diagram to illustrate the motion of one of the smoke particles, so just one of it. So please do not draw all these curly lines to show that it's random. Rather, because they are bombarded at different times by different number of air particles, so you can use straight lines. So you might also want to add in the arrows, but make sure the arrow direction do not contradict each other. So this one I went through already. Explain why smoke particles are used to illustrate Brownian motion. Smoke particles have small mass, so it will move easily when bombarded by lighter invisible air particles. Now, it is also large enough to be visible under a microscope. So another substitute for smoke particles is flower pollen. In fact, this is the one that Mr. Brown observed, is the flower pollen that is suspended in liquid, in water. Now, using simple kinetic theory, explain the motion of the smoke particles, part C, part 1. Now, the smoke particles are in continuous random motion, okay, but this is due to the frequent bombardment or collision by invisible air particles, which are initially also in continuous random motion. Now, how does the air exert a pressure on the walls of the cell containing it? This is a popular question. Now, the air molecules will collide frequently and forcefully with the inner walls of the cell, exerting a net force. Okay? Then, how to get the second mark? Since pressure is force per unit area, therefore, the gas will exert a pressure on the wall. Okay? Now, what is the effect of raising the temperature of the air in the cell? So we assume that the volume in the air cell remains the same. When the temperature of the air is raised, the average Ke of the air molecules increase and they move faster. Okay, so if they move faster, that means they will collide more frequently and more forcefully. Okay, so in fact, this is written in the next page. They collide with the smoke particles more frequently and more forcefully. Therefore, the smoke particles will move faster and change directions more frequently. Okay, so they're asking for the effect of raising the temperature. But some students did not, some students will not write about the smoke particles. They'll talk about the pressure of air in the cell. Okay. So when I increase the temperature of the air in the cell, the pressure of the air in the cell will increase. Okay, why? Because they collide more frequently and more forcefully with the inner walls. With the inner walls of the container of the cell. Okay, so sometimes I'll see two answers. The first one is talking about the pressure of air in a cell increases. And the other one, because it is still on this Brownian motion, so they will talk about the smoke particles changing direction more frequently and moving faster. Okay, but this is all due to the invisible air particles. Okay, question 5. For fixed mass of gas at a constant volume, so volume is constant, mass is constant, it is observed that the gas pressure increases with temperature. Okay, which of the following statement may explain this observation? So actually there is this formula that you may want to search up on the internet. Is PV equals nRT. Okay, now P is actually your pressure, your V is your volume, and capital T is actually the temperature. So they actually have this relationship. Okay, so let us try to put all this inside. We know that the mass is constant, the volume is constant. Okay, so we put a volume constant, and it is said that the gas pressure increases with temperature. That means as temperature increases, pressure will increase, right? Because these two are actually constants. Okay, so they will just stay the same. And because P, V, and T, there are three variables. In this case, volume is fixed. And if I increase the temperature, and on the left hand side, the pressure must also increase. So why is that so? So with this formula or with this relationship, you can see what happens when temperature increases, right? When temperature increases, the pressure increases. But it still doesn't explain why the pressure increase. So we must go down into the kinetic model of metal. Okay, so when temperature increases, right, what the Ke and the speed of the particles will increase. And with that, the frequency and force of collision with the inner walls will both increase. Okay, so let us take a look at the options. Molecules collide with the container walls more forcefully and frequently. That is true, right? Like what I talk about here. The molecules collide with one another more frequently. Yes, they will collide with one another more frequently, but so this is a true statement, but they do not contribute to the pressure in the container, because the pressure in the container must be coming from the force of collision between the particles and inner walls, okay, and not between the particles themselves. Okay, so this one, although it's a true statement, but it does not explain why gas pressure increase. So I say again, the gas pressure comes from the force of the particles on inner walls. Okay, so the particles must collide with the inner walls before they can exert a pressure or when they collide with the inner walls, they exert a force. Force over area gives us the pressure. It is not about the particles colliding with one another inside. Okay. Then of course 3 is not true. They combine into bigger molecules before colliding, so that is not true. So answer is A, right? When temperature increases, Ke and speed increases, so the frequency and force of collision actually increases. Okay, question 6. A fixed mass of gas, M is fixed, is enclosed in a vessel with a movable piston. That means the volume can change. Okay. The piston is lowered so that the volume of the gas is reduced. So when volume decreases, okay, the frequency of collision will increase, right? Because there's lesser space for the particles to move, so they'll collide with the inner walls more frequently. Okay. Oh, sorry. Okay, the volume actually decreases, so frequency of collision increases. Now, using the idea of energy transfer, explain what happens to the speed of the gas particles as the piston lowers. So the energy is transferred from the piston to the internal store of the gas as the moving piston does work, right? What is work? Work done is when we exert a force and the object moves in the direction of the force. So in this case, when we are pressing down on the piston, we exert a force, right? We transfer the energy to the internal store of the gas because the moving piston made the gas particles move in the direction of the force. So average Ke of the gas particles increases, therefore the particles move faster. So what happens, if any, to the temperature of the gas as the piston is lowered? So the temperature of the gas increases as it increases with the average Ke of the gas particles, right? So this is linked to here because I exert a force, I transfer energy to the particles because I'm doing work, right, by making the particles move in the direction of the force. Okay, so the Ke actually increases and therefore the temperature of the gas increases. Okay, part C, a little bit change. The vessel is now heated externally and the temperature of the gas rises. Just now it was when I push the piston and the temperature of the gas actually increases. But now I heat it up externally, so the temperature of the gas rises. Okay, and when that happens, the Ke and speed increases. Okay, the Ke and speed of the particles increases, and this will lead to the frequency and force of collision to increase. Okay, so they want us to use the kinetic model of gas, account for the increase in volume of the gas. So now the volume actually increases. So when temperature of the gas increases, average Ke of the gas particles increases. Okay, and the gas particles will now move faster and collide against the inner wall more frequently and more forcefully. So you need these two factors. So the net force per unit area, which is actually the pressure, okay, is greater than the atmospheric pressure because there is actually atmospheric pressure pressing down on here. Okay, I'm no longer applying a force, but there's atmospheric pressure. Therefore, there will be a resultant upward force acting on the piston that causes the piston to move upwards and increase the volume of the gas. Now, when will this volume keep on increasing? Well, it depends, right? Because when I increase the volume, right, when volume increases, it actually lowers down the frequency of collision. Okay, so you might also want to take into account this. Okay, what happens when the volume increases? Okay, question 7. Using a kinetic model of gases, explain why the pressure exerted by a fixed mass of gas increases when its volume is reduced at constant temperature. Okay, so now there are a lot of factors. Let's take a look. Why does the pressure increase? So they tell us the pressure increase. They want us to explain why. What happens to cause this? Reducing volume and temperature to be fixed. So remember the relationship that I wrote just now, PV equals to nRT. Okay, because nR is a constant, we will not care about that. So now the volume actually decreases, and I can see that the temperature remains fixed. So from this relationship, right, when volume decreases, pressure actually increases. Okay, so we can actually sort of verify that this is true because of this relationship, PV equals to nRT, right? But now we need to use kinetic model to explain why is this happening. Okay, so the answer is this. When the volume is reduced, the number of particles per unit volume increases. There are now more particles in a certain volume. So this is a very useful phrase that you might want to take note of. It causes then the gas particles to collide against the walls of the container more frequently, but not more forcefully. It's the same force because there's constant temperature, right? Okay, so the change in volume actually only results in the frequency of collision. In this case, the volume decreases, the number of particles per unit volume increases, and therefore the frequency of collision increases. Now, what happens then? As pressure equals to force over area, when the net force per unit area, right? Remember, the particles are now colliding with the inner walls more frequently. So the net force that they exert per unit area actually increases. And since pressure equals to force over area, the pressure then increases. Okay? Okay, question 8. The following table describes the relationship between pressure, volume, and temperature. So we actually have this PV equals to nRT, right? Nowadays, it's not really taught in the syllabus, but I find it useful to remember this relationship. Okay, so let's take a look. This is actually answered by row 1, row 2, row 3. Okay, so in row number 1, the temperature is constant. Okay, so I take note of this. The average KE is then constant, right? Because temperature affects KE or KE affects temperature, right? And they tell us that the pressure increases. So if I were to use this relationship, right, I can see that the volume actually decreases. Okay, the volume decreases. And what happens to the average distance apart between the particles will also decrease because now the amount of space that the particles can move is lesser. So they are much closer together. And when they're much closer together, the frequency of collision increases. And therefore, the force that they exert on the inner walls, right, the average force that the particles exert on inner walls actually increases. Therefore, right, we have frequency increasing, therefore the pressure will increase. Okay, let's look at row 2. Okay, so they tell us that the average KE increases. Right, this is in the question. Therefore, I can write that the temperature increases. So PV equals to nRT. Okay, these two are constant. Now temperature increases. Okay, and they tell me that the pressure is constant. So with that, it means that the volume must increase. Correct? You can see from this relationship, right? So the temperature increases, the pressure is constant, right? So what happens to the volume? The volume actually increases. If the volume increases, that means the average distance between the particles increases. Therefore, the frequency of collision actually decreases, right? Because now they have much more space to move about, so the frequency of collision will decrease. Let us look at row number 3. Okay, so they started off with temperature decreasing. So I have PV equals nRT. Temperature decreasing, and they tell me that the volume is constant. Okay, so I compare this side and left hand side, right hand side. Right hand side, nR is constant, T went down, so therefore if V is constant, P must go down. So what happens over here? If temperature decrease, average KE will decrease, right? And they are telling me that the volume actually is constant, so the average distance between the particles will remain constant. Okay, and I see that the pressure decreases. Why is that so? Because as temperature decreases, there are two effects: the frequency of collision and the force of collision, they will decrease. Okay, but because so the frequency of collision will decrease. So even though the volume is constant, but because they are moving much slower. Okay, so therefore, overall, the pressure will decrease. Okay, so to summarize what we have learned so far, it is good to memorize this formula, but you can only use it to help you see what happens when temperature increase, what happens when volume decrease, so on and so forth. So what happens to the pressure, okay? But you cannot use it to explain. When they ask you to explain using kinetic model of metal, you must talk about the force of collision, you must talk about the frequency of collision. Okay, question 9. It shows a stationary piston in a cylinder. The gas in the cylinder exerts the same pressure on the piston as it does on the sealed end. The sealed end has a smaller cross-sectional area. So this area is smaller. I call it A2. This area is larger. So A1 is larger than A2. Now use your ideas about the molecules to explain why the pressures are the same. Okay, so although the sealed end has a smaller cross-sectional area than the piston, the average Ke of the gas molecules is the same, right? And the frequency of collision per unit area at both surfaces remain the same, right? Because this only has a small area, okay? But the frequency of collision over here, they have lesser particles, right? But lesser area. Here we have more particles but more surface area. So the frequency of collision per unit area at both surfaces remain the same. Since pressure equals to force over area and net force per unit area remains the same, so both the piston and sealed end will experience the same pressure. You have actually learned in pressure, right? Previous chapter, that the pressure remains the same in a sealed container. Okay. Okay, question 10. Figure 10.1 shows air in a cylinder at room temperature. The piston is free to move and now it's occupying 30 cm3. Now, when the cylinder is placed in a very cold freezer, the piston moves inwards. That means the volume decreases. And in a cold freezer, so your temperature decreases, your volume decreases. So 10.2 shows the position of the piston after it has stopped moving. Okay, the pressure in the air in the cylinder in 10.1 is the same as the pressure in 10.2. So if I call this P, this will also be P. Okay, it is important to note that there is external pressure, which is, let's say, PATM and PATM. So in figure 10.1, pressure inside the piston, pressure of the air in the piston is equals to PATM. Similarly, in 10.2, even though the volume decreases, the pressure of air inside the piston is also equals to PATM. Okay? So using kinetic theory, explain how the molecules in the cylinder creates a pressure. So this is a standard answer. The air molecules collide frequently with the walls and they exert a net force on it. Since the pressure is force per unit area, the gas exerts a pressure on the wall. So usually this is a 2-mark question. Okay, how does it create the same final pressure in 10.2 as compared to figure 10.1? Okay, in figure 10.2, the air molecules with lower temperature has a lower average speed and lower Ke, okay, as compared to 10.1. Therefore, they collide with the inner walls less forcefully. Right? If they collide with the inner wall less forcefully, there will be a resultant force that causes it to move inwards. Right? It causes it to move inwards. Therefore, the volume actually decreases. But then, remember just now I told you that volume decrease, there will be an effect. Due to a smaller volume, the number of air molecules per unit volume is higher. Okay, so the frequency of collision actually increases. So it's a little bit contradicting, but let me explain. So maybe I write this part first. As the temperature decreases, okay, so the frequency of collision decreases, the force of collision decreases, and this will lead to pressure inside within to decrease. And since it decreases, it is less than PATM, right? So P is less than PATM. Therefore, there will be a resultant force that pushes the piston inwards, and this will decrease the volume. Okay, this will decrease the volume. Okay, and so far we talk about the pressure decreasing lesser than PATM. But why is it that in figure 10.2 the pressure is now back to equal to PATM, and that the pressure in the figure 10.1 is now equals to 10.2? Because there is now this volume decreasing that we need to take into account. So what happens when the volume decreases? When volume decreases, it will lead to number of particles per unit volume to increase, and this will lead to the frequency of collision to increase. But just now we say that the frequency of collision decreases because the temperature decreases, right? So now, because of a change in volume, the frequency of collision is now actually even larger than before, right? This change is actually now bigger. So now it's actually able to sort of balance off the effect due to the force decreasing. So now the pressure inside will be the same as before, even though the volume has decreased and even though the temperature has decreased. Okay, so let's read this again. In figure 10.2, air molecules with lower temperature has lower average KE and move slower. This one I think quite easy to understand. And they collide with the inner walls less forcefully. Correct, right? And we also then shift to here. Because the pressure less than atmospheric pressure, there's a resultant force, therefore volume decrease. And this leads us to the third paragraph. When now that it has occupied a smaller volume, the number of air molecules per unit volume is higher, right? And therefore the frequency of collision is now higher than even in figure 10.1. Okay, so this is the most difficult kind of question. Okay, and this question falls under constant pressure. You see that the pressure did not change. Okay, and this is by a dynamic this is very dynamic. This is like the piston is able to move. Okay, so this is the most difficult question. Now, as the air particles in figure 10.2 collide less forcefully, agree, right? Less forcefully, but more frequently because of the smaller volume, the net force exerted per unit area is the same as figure 10.1, therefore pressure is the same. Okay, so you might want to star this question because this is really one of the most difficult question in this chapter. Okay, so now explain in terms of pressure what causes the piston to move inwards. So we already explained that because the pressure within is less than atmospheric pressure, therefore there's a resultant force. Okay, so this is really the toughest question. You might want to check with me if you are not able to understand it.